Of what?
Of the word.
Oh, I don't know. I don't know what it means. It could be like more offensive. Like there are certain words that I would not say.
So if you remove
In
the N
English,
and you
even.
replace the O with an A, then it's the bad word.
Yeah.
But if you use punto, which is P-U-N-T-O, it's point.
Yeah.
The other one is
It's totally fine.
the equivalent of...
That's like you can say duck and everybody's cool with it, and then as soon as you say the other one, everybody gets mad. It sounds different. It sounds like practically the same, but people get offended. I don't know. I don't have tenure yet. I'm trying to keep on the straight and narrow, man.
We'll put a good review.
Thank you. I appreciate that. Yes. Yes. Only super clean fun. Always dad jokes. Very professional. Yes. Yes. Zero profanity. Needs more profanity, probably. It would be better if there was a lot of profanity in this lecture. Yes. Okay.
It's more realistic.
Yeah. I haven't gotten in trouble. I have had somebody at a meeting say to the whole staff, like, been hearing that there are like some swearing in class from the professors, and like something like how that's like not great. And I'm like, I think it's part of the lesson. I mean, it's like you guys would be less interested if I didn't drop a little F-bomb every once in a while.
Definitely gets your attention.
Yeah. So it's, yeah. Okay. Good. Okay. Good. I try not to be offensive with it. Like there are really easy ways to be offensive with language, and I'm trying not to be offensive with it. I'm just trying to like be fun with it. Fun with language. Enthusiasm. I like it. Okay. So, speaking of awesome things, how do you say 10 in Spanish?
Yes.
10. 10.3. Tres? Tres? Tres. What? Yeah, I took French. I don't know. Now the true power of impedance-based modeling is revealed. We're nothing if not a little bit grandiose when we talk about things. We can skip a time domain model, time domain models being, for instance, state-space models or input-output differential equation models, and derive a transfer function model directly. Okay? That's what these impedance-based methods can get us. But before we do, let's be sure to recall that a transfer function model concerns itself with the forced response of a system, ignoring the free response. Remember when we derived the transfer function, from the input-output differential equation, we took the Laplace transform. There were some terms that pop up when you take the Laplace transform that have to do with the initial conditions, right? We set those to 0. We said the transfer function is not going to consider the initial conditions in it. Therefore, we have no access to the free response, only the forced response, only the response of the system to inputs. We don't have any information about the response of the system to initial conditions. Therefore, once you have a transfer function, you don't have that information in there. So, if we care to consider the free response of a system, we can convert the transfer function model to an input-output differential equation and solve it there. You might say, that's kind of weird because you know you can use the Laplace transform to solve differential equations, right? To solve input-output differential equations. So why would we go from a transfer function, which is in the Laplace domain, to an input-output differential equation, and then turn around and take the Laplace transform again? Well, it's because we set those terms to 0 before, so we'd have to go back and do it right? That's like kind of the idea. It's like you have a transfer function, you already set those terms to 0 with the Laplace transform. If you need to know what's going on with the initial condition aspect of the system, the free response, then you need to go back and go back to your differential equation form. So there's that. So that's just like something to keep in mind before we get too far down this path. There are two primary ways impedance-based modeling is used here to derive transfer functions. The first and most general is described in this lesson. The second is a shortcut, most useful for relatively simple systems, described in lecture 10.5. I actually think that most of the value of the impedance-based modeling methods, though, is found in the shortcut method. So whereas I'm usually not a proponent of so-called shortcuts, I am in this case because I think that the real point of doing this impedance-based modeling is to do, the main point is to have a sort of shortcut to a transfer function model. And the shortcut methods will get us there very quickly. Whereas this method that we're going to learn in this lecture is actually practically like doing the entire state space model derivation, that whole algorithm that we learned. And if you're going to do all that work, you might as well just get the state space model from which you can derive the transfer function anyways. So I don't know. For me, it's not like this lecture, the method in this lecture it's good to know it's there, but it's also, if you're going to do the full thing, you might as well just go back to solving for the state space model. But that's my opinion. It's kind of a matter of preference. So, good. In what follows, it is important to recognize that in the Laplace domain, every elemental equation is just the across variable is equal to the through variable times the impedance of that element. Okay? So in the case of a capacitor, it's, I've got this weird color working on here. Well, it's just hard to see it. For a capacitor, it would be like VC equals IC, so the voltage related to the current, times ZC, which is 1 over CS, right? So that's the elemental equation for a capacitor. So this is always the elemental equation. It's always the same thing, but with different impedances plugged in, right? Different cross-through variables and different impedances. So this algorithm is very similar to that for state space models from linear graph models. So that's the one we presented in lecture 3-4. Very familiar. We learned that. We spent a lot of time doing that, actually last semester. In the following, we consider a connected graph with B branches, of which S are sources. There are 2 B minus S unknown across and through variables, so that's how many equations we need in order to solve for all of the unknowns. We have B minus S elemental equations, and for the rest we will write continuity and compatibility equations. N is the number of nodes. So this is going to look just like what we did back in chapter 3. So derive 2B minus S independent Laplace domain algebraic equations from Laplace domain elemental continuity and compatibility equations. Previously, it would have been time domain, and it would have been differential and algebraic equations. That's the only difference to what we did. The process looks the same. Draw a normal tree from the linear graph. So we've got that. It's the same as before. Write a Laplace domain elemental equation for each passive element. That's different, but only in as much as all of them are the same equation. V cross variable equals through variable times impedance. So that's even easier than before. You may recall that we did something like this in electronics back in the mechatronics course, where we were doing, we went from looking at time domain to impedance-based modeling, right? And we said, oh yeah, now we have not just Ohm's law, but generalized Ohm's law, where we have every elemental equation just being generalized Ohm's law. This is like generalized Ohm's law. This is generalized squared Ohm's law.
So, overgeneralized.
Yes. Super generalized. Hyper generalized. Uber generalized. Yeah, I think that works. Okay. It's a very multicultural lecture today. We have Spanish. Uber is something like German, maybe. I think it's German, right? Uber? What? Yeah, like the Ubermensch. That's just kind of racist, though. I mean, the Ubermensch is not, but then a lot of people took it to be, and so it kind of is now. Nietzsche, he definitely got into some trouble, that guy. All right, so write a continuity equation for each passive branch by drawing a contour intersecting that and no other branch. So that sounds exactly like what we did before, right? Same as the procedure before. Write a compatibility equation for each passive link by temporarily including it in the tree and finding the compatibility equation for the resulting loop. Exactly the same as before. So the only thing that's different is like kind of one point B, but everything else is identical to how it was before. And then step 2, solve the algebraic system of 2B equations and 2B unknowns for outputs in terms of inputs only. It's an algebraic system, so you guys have been solving, and it's also linear. So, I mean, assuming that you have a linear model, which we typically do, it's algebraic and probably linear, and so you guys have been solving linear systems of equations for as long as you remember, right? It's been a minute. You guys have been doing this. So not too bad. You can use the fact that you can eliminate half your variables right away by substituting in, eliminating secondary variables in that first nice substitution of your continuity and compatibility equations like before. That's one way to go. Sometimes solving for all the unknowns via the usual methods like linear algebra methods, for instance, is easier than trying to cherry pick the desired outputs. Other times, cherry picking the desired outputs is faster and you can do that. Step 3, the solution for each output yi. We're gonna get a little bit into subscript hell for a moment, but like bear with me. So try to stick with me. I'm gonna read it and we'll try to parse it again. So solution for each output yi depends on 0 or more inputs uj. So what this is going to look like is you're going to have like say yi equals say something times like u1 plus something else times u2, which is not a good band by the way, plus something times u3. I don't know why people like them.
I'm offended.
Oh, I'm sorry.
No, it's okay.
Not sorry. Not sorry.
Sorry.
Okay, so so to solve for the transfer function yi over uj, set all of the other u's to 0, and then divide both sides by uj. So what I mean is, if you want to know, let's just say this is some specific y. We'll call this y3. If you want to know the transfer function, what is the output y3 over the input u2? Anything over u2, in my opinion. But then you set all the other u's equal to 0 for a moment. So you go 0, you go 0. Those terms go away. And you divide both sides by u2. And whatever this term is, we'll call this term star. You get right there. That's your transfer function. So not too bad, right? Okay. Let's do the linear graph model of this Firehose example real quick. I don't really know how I know that fire trucks, they usually don't supply the water. There's a fire hydrant. She's on it. She does all of the bless yous in this class, and she's been nailing it. This is like 6 months straight. She's really good. Yes. So fortunately, we've had no demons enter any students after they've sneezed. It's been good. So I don't know, fire trucks, they definitely do carry some water on board and some reservoir, and they got a little hose and they can do like little brush fire or something outside the road. Anyways, let's say that that's what's going on here. You have a tank of water. I don't know how it works, but definitely there's a tank of water, and definitely they have probably some pump that's pumping it up to some higher pressure than whatever the tank's giving it, right? So a pump that's pumping up the pressure, and then the hose will model as being some fluid inertance and resistance. And we'll ignore any height gain here. So like the pressure head that's developed here, we'll ignore it because I think that most of the time you shoot from the hip, which is pretty low. Not too bad. Yeah. Yeah. I mean, if I was a fireman, that's what I would do. A firefighter. So let's do the linear graph. The other part about my classes is they tend to start late and go late. It's a really good feature of them. And if people show up late, it's just, we're we're really bad at being like on time to anything. So we've got a pressure that's definitely going to be built up at the bottom of this tank, right? Because it's got some height column of water. So that's this fluid capacitance C. We've got a pump that's going to increase the pressure, right? So it's going to drop that way from the pressure from the pump. So the pump's going to have a pressure source model here. And then we've got this hose that goes to atmosphere, right? Out here, P atmosphere. Up here, P atmosphere. And this P atmosphere. So it goes through an inductance, L, or inertance, right? And it goes through R, the resistance, to atmosphere. Now let's also do we'll do the first step. So 1A was to draw the normal tree, right? Normal tree, the cross variable source is going to be included in the normal tree. Ooh, we'll use a color. Okay, and then we'll be done. We'll use a color.
Teal.
Teal?
Teal's where it's at.
Oh man. What happened? Happened to my colors? Here. There we go. Teal, you say?
Yeah, like right in the middle. There you go.
Okay. Okay. Now, the pressure source. Yeah? Ooh, that looks nice. I like it. That's a good choice. That's a good choice. Okay, and then we've got the A-type energy storage elements, the capacitor. And then the D-type energy dissipative element, the resistor. And then if we added anything else, it would create a loop. Remember that all the nodes are included implicitly, even though we didn't draw them in. There we go. So we have our normal tree. On Friday, we'll pick it up from there, and we'll finish this problem.